Hello everyone. In today's lesson we're going to be looking at characteristics of the periodic table, and we're going to start out by looking at the arrangement of the periodic table. So we all know that the modern periodic table is arranged into horizontal rows, and we call those horizontal rows periods. On our modern periodic table there are 7 periods going from top to bottom. And we also see on the periodic table then vertical columns. And these vertical columns, we refer to these as groups or families in chemistry. So the modern periodic table is arranged in order of increasing atomic number. We start at the top left, go from left to right, atomic number 1, atomic number 2, go down to period 2, 3, 4, 5 through 10, and so on. When we arrange the elements in order of increasing atomic number, what we find is that the properties of the elements tend to repeat themselves such that the elements in the same column, the elements in the same group or family have similar characteristics, similar properties. So let's take a look at one group or family here. Let's take a look at the elements in the oxygen group, or the column in the periodic table that starts with oxygen here. So we're looking at the 16th column on the periodic table. So as I said earlier, when arranged in order of increasing atomic number, we expect that the elements in the same columns, the same group or family, will have similar chemical characteristics, similar properties. And this is in large part due to the fact that the elements in the same column have the same number of valence electrons. So if we think back to what we learned in Chapter 5, talking about electrons and electron configurations, and thinking about how we can use the periodic table as a shortcut to help us write electron configurations. If we think about oxygen, so let's focus just on the first element in that group, column number 16 there. If we want to write the electron configuration for oxygen using the shortcut with the periodic table, we can think about hydrogen as 1s1, helium as 1s2, lithium is 2s1, beryllium is 2s2, boron is 2p1, carbon 2p2, nitrogen 2p3, and oxygen 2p4. So if we write the noble gas configuration, then we go back to the first period, and the noble gas at the end of that. At that row is helium, then we had 2s2, 2p4 as our electron configuration for oxygen. What we find is that more generally, the elements in this column, in this group basic valence electron configuration of s2p4. In other words, all of those elements in group 16, the oxygen group here, have 6 valence electrons. So if we were to write the electron dot structure for any of these elements, it would have 6 valence electrons, like so. And that would be the same for sulfur and selenium and so on. So the fact that these elements in the 16th column of the periodic table all have 6 valence electrons, they all have the same basic valence electron configuration. It means that they have similar properties, similar characteristics. So you could expect oxygen and sulfur to react in similar ways. And this is really one of the most useful characteristics of the periodic table, this fact that elements in the same column groups or families, as we said earlier, they have similar characteristics, similar properties. And in fact, this repetition of properties is referred to as periodic law. So what we want to take a look at next is how some of these groups or families in the periodic table share properties, but not only that, how other groups of elements maybe share some similar characteristics. So we're going to be looking at different ways that we can describe the different regions of the periodic table. And we're going to start with a discussion of metals versus nonmetals. So on many periodic tables, what you're going to find is that there is this stair-step line that starts, well, technically it starts right over here underneath hydrogen. And then it goes over here underneath boron, and then down underneath silicon, down, and so on in this fashion until we get right down here to the left of astatine. And again, this is going to be highlighted on many periodic tables. Doesn't have to be highlighted on this periodic table, so we've drawn it in for effect. This stair-step line separates what we refer to as the metals on the periodic table from the nonmetals. So let's start out here today talking about the metals. Everything below and to the left of that stair-step line. So all of the elements over here in the S block except for hydrogen, every element here in the transition block, the D block as we've discussed previously in class, down here in the F block, all of these elements, and then we've got the elements over here. These are all referred to as metals. So you probably know a little bit about metals just from prior science classes or from personal experience. Just some typical characteristics of metals. Many of them do tend to be shiny when they are smooth and clean. Many of them, nearly all of them, do tend to be solids at room temperature. Oops. Sorry about that. What else? What else for metals? Let's see here. So we've got shiny, we've got solids at room temperature. How about conductors? Metals tend to be good conductors of heat and electricity. And they also tend to be malleable and ductile. So these are some general characteristics of what we refer to as metals, which would be below and to the left of that stair-step line on the periodic table. Now, the elements that we find above and to the right of that stair-step line, so let's get rid of our properties for metals here and talk about the other elements that we find above and to the right of that stair-step line. Use a different color highlighter. Let's go with blue. So these elements over here are nonmetals. Now, first thing you'll notice is that there are fewer nonmetals than there are metals. Some other characteristics of nonmetals, typically either going to be gases or brittle solids. There are exceptions, but we do see that many of these nonmetals are either gases or brittle solids. Also, typically poor conductors of both heat and electricity when we talk about nonmetals. Now, what about these elements that lie right here on that stair-step line? They lie on the boundary between the metals and the nonmetals. So let's highlight a few of these elements in particular. We're going to use red for this. I'm going to focus on boron, silicon, germanium, arsenic, antimony, tellurium right now. So these 6 are sort of what are referred to as the classic metalloids or semi-metals. We'll talk about a couple of other elements that may or may not be included in this group in just a second. But these 6 in particular are nearly always classified as metalloids. So they lie right along that stair-step boundary between the metals and the nonmetals, and as a result, they have some properties of both, properties of metals and nonmetals. So they don't fit nicely into either category. So what you're going to find in this group are some semiconductors, like silicon and germanium in particular, which can be made to conduct electricity when they're given small boosts of energy, and it makes them very, very useful in electronic circuits. A couple of elements that we didn't talk about that also lie along this stair-step line. Technically you could say hydrogen is on that stair-step line. Hydrogen is without question. We didn't actually highlight it earlier, so let's fix that. Hydrogen is unquestionably a nonmetal. It belongs over there with all of the other nonmetals. Aluminum I highlighted earlier in yellow, but let's make it just a little more clear. Aluminum is on that stair-step line, but its characteristic properties are similar to those of the metals. So aluminum is nearly always classified as a metal. You're unlikely to see aluminum be classified as a metalloid. That leaves us with 2 elements. Let's do those in a different color down here. Let's go with, purple, violet for those 2 down here. So we have polonium and we have astatine. Depending on the source, some textbooks may list polonium and or astatine as metalloids. Usually astatine isn't really put into a category because we just don't really know enough about it. There isn't enough of it out there for us really to know how it reacts. We would predict that it would be similar, of course, to those other elements in group 17, the halogens, in terms of its reactivity, but we just don't know. We just don't have the experimental data to come to that conclusion. So some people include astatine in that metalloid group, similar with polonium. Whether or not polonium is technically a metal or a metalloid, it's going to depend on the source. So we're really going to sort of focus on those 6 here in red and focus on those when we talk about metalloids. We'll treat astatine just as a nonmetal for all intents and purposes. Same thing with polonium, except we'll treat it as a metal for the most part. But again, depending on the source, different textbooks, different websites may list polonium and astatine as part of the metalloid group. So that's one general way that we can sort of divide the periodic table based on elements with similar characteristics in terms of nonmetals versus metals versus metalloids.